So this is the second part of the video. I just was writing this out, and now I'm going to talk about how you're actually going to apply the telescoping series test. So really what's happening here is that I have some terms canceling. I have this negative 1/2 is going to cancel with my positive 1/2. This negative 1/3 is going to cancel with positive 1/3. And this is going to happen. This is going to keep happening. Notice, however, that my 1 doesn't cancel. That's going to be important for later. So now let's look at the nth term, because this is what's going to be really essential, because we can take the limit of the nth term since it's a variable. Notice how this later term, which is 1 over n plus 1, is going to cancel with your 1 over n from the future. So I like thinking about tenses in the sense that I have 1 over n plus 1, which is going to be the same as my 1 over n from the future. So what happens here is that my 1 over n from the future would have already canceled with my 1 over n plus 1 from the past. And so if that makes any sense whatsoever, I'm really left with 1 plus negative 1 over n plus 1. And, sorry, I'm actually going to, that's not true. I forgot that I had these equal signs interconnecting everything. Actually, it's equal to the limit as n approaches infinity of 1 over n plus 1. Now, this is where the telescoping series test comes in. If this limit is a finite number, then the series is going to converge. If this limit is an infinite number, such as infinity, then this series is going to diverge. And if you think about this in your head, it really makes a lot of sense. So if this were infinity, then the sum of my series is infinity, since this is like the infinite term. So that means that it's diverging, since the sum of it is infinity. But if this is a finite number, that's as n approaches infinity, we're getting a finite sum value. So that tells us that the series converges. And as you expected, this series also gives you the sum. You can also take the sum. Obviously, I have the sum set up right here because I have the summation notation. The sum is equal to that. So if I can find the limit, I can find the sum. I can also find whether it converges or diverges. So the first thing that I'm going to do is actually show whether this converges or diverges. So I'm going to take this limit off to the side. Limit as n approaches infinity of 1 divided by n plus 1 gives me limit as n approaches infinity, 1 over infinity plus 1, which is the same as 1 over infinity, which is the same as 0. So because my limit is 0, and 0 is finite, I can say that this sum is 1, and the series converges by the telescoping series test. Really, just to backtrack a little bit and explain this a little more, we started with this original series. I recognize that I can't use the nth term test for divergence, I can't use the geometric series test, and I certainly can't use p-series because we can't combine those. They're not like terms. So what I did was I split up into partial fractions, and I couldn't find the numerator, so I solved for the numerator by multiplying by the denominator. That gave me this equation, and I was able to solve for a and b, which allowed me to set up a new series equal to the actual problem, which was this, and I was able to expand that series and recognize that a pattern was occurring. There was this pattern happening which allowed me to come up with the nth term, and after I took the limit of that nth term, I was able to say that since that limit was 0, the series converges, and the sum of that series is 1, as I showed, that the sum equals 1. Okay, so next example, we're going back to the geometric series test. we have this random decimal that repeats to infinity, and the problem wants us to first write the decimal as a geometric series, then write the decimal as a ratio of two integers. So this problem really helped me out a lot. Sometimes these types of problems don't even tell you that this first step, that they'll just ask for a ratio of two integers, and you'll have to know that you're going to have to make it a geometric series first. And so this problem is really taking us step by step through. And the first part, though, the challenge is, how do we get this decimal as a geometric series? And one of the best ways to do that, perhaps the only way, definitely not the only way, is by making it a sum. So we can say that this repeating decimal is equal to 0.075 plus 0.00075 plus, and that keeps extending into infinity. So notice how you can keep adding this and you'll end up with this number. So that's basically what I'm saying. Now in this next step, I'm going to rewrite these as fractions just to make my life a little simpler, and some cool things will happen when I do so. So this is equal to 75 over 1,000. And this next decimal is 75 over 100,000. Now, next step, I'm going to pull out my 75 just to make life a little bit simpler. And in this next step, I'm going to recognize that there's a pattern happening. And that pattern is that I can write this as powers of 1 over 1,000. So 1 over 1,000 squared gives me 1 over 100,000. And so from this point, you should realize that you can write this as a geometric series. This is my A value, and this is my R, and that's my N. So I can say the sum as n goes from 1 to infinity of my A value, which is 75, times 1 divided by 1,000 to the nth power. Notice that I started the index at 1 because this was to the power of 1, not 0. If there had been a 1 term, which there wasn't, then I would have to start it at 0. So it also wants the decimal as a ratio of two integers. And so I can actually do that by taking the sum, which is going to give me a ratio, like one number over another number. And I can say that my sum is equal to A divided by 1 minus R. So remember, in the previous video, I talked about how A is always your first number in the series. So in this case, the index is 1, so that's our first n value. So when I plug in 1 for n, I get 75 over 1,000. 75 times 1 over 1,000 raised to the first power. So I'm going to write 75 divided by 1,000, and I'm going to put that over 1 minus 1 divided by 1,000. Okay, I'm quickly approaching the 10-minute mark, so I'm going to speed this up a bit. We get 75 over 1,000 divided by 999 over 1,000. And I'm just going to rewrite this to get my actual ratio. I mean, I have the unsimplified ratio. So I just expanded this out, and I ended up with 75 over 999. And if you look carefully at the problem, you can notice that the pattern is simply getting my repeating part over how many how many decimal spots it takes up. And that's really the trick to doing that. But most of these problems actually want to see all of this work because you're graded off of the work and not the answer. So I would strongly recommend doing all of this work when in doubt. If you're in a calculus class. Obviously, this is a nice trick if you're not in calculus, just to get straight to the answer, but I would definitely recommend doing this process. So I really hope that you learned something from this video, and please comment if you have questions. Thank you so much for watching.